Now we're going to define what are called independent events, and we'll look at some examples. So first, two events are defined as independent if the joint probability of E and F is equal to the product of both of the individual probabilities. Otherwise, we call them dependent events. And we're going to show using this definition that if E and F are independent, then the probability of E given F will simplify to just be the probability of E. And similarly, the probability of F given E will simplify to just be the probability of F. So intuitively, it means that knowing information about my event F doesn't change or provide any new information about the probability of E. Let's see where that second definition comes from. So again, conditional probability, here's my definition of conditional probability. But if I have independent events, the numerator can change into the product of these two, and I'll get cancellation with the probability of F in the denominator, leading us just to the probability of E. So again, knowing that F happened doesn't change our belief that E happened. So it turns out you can actually use either of these. So I'm going to write independent events, E and F, if and only if either of these holds. You don't have to check both since they're related to one another through that proof. And typically whatever one you want to use to check is just whatever information is easier for you to have to find. So let's do it in an example here. Suppose I flip a fair coin twice. Let's define my event H1, that the coin lands on heads on the first flip. The event H2 is the coin lands on heads on the second flip. Are these independent or dependent? Okay, so intuitively, knowing that I got a heads on the first flip doesn't change anything about the coin. So it wouldn't change anything about the probability that the second flip would be heads versus tails. And so intuitively, I would expect these to be independent. But let's prove it mathematically, because sometimes our intuition's not always correct. In this case, it is correct. This is independent, but let's prove it. So I'm going to think of my whole sample space first. Let's write it as a set here. So I could get heads first, heads second. I could get heads first, comma, tails second. I could get tails first, head second, or tails, tails. That's my entire sample space. And so if I want to think about, let's think about the joint probability first, the probability of H1 and H2. Well, that's only one out of the possible 4 outcomes. And then separately, I'm going to have a question mark here to say, is this the same as the individual, or the product of the individual probabilities like this? Okay, well, let's go do those on the side. The probability of getting heads first. Well, it's either heads or tails. It's 50-50. That's a 1 out of 2 chance. But I can also see it here by realizing there's 2 outcomes out of the 4 that have heads first. So 2 out of 4 are 1/2. And similarly, if I get heads second, 2 out of the 4 outcomes have heads second. So again, a 1/2 probability. And this is therefore 1/2 times 1/2. So I'm going to write this as yes. So therefore these are independent. H1 and H2 are independent. And sometimes you'll see us use this notation where we do a double bar like this and straight line. And H2, this also means independent. Okay. Let's move on to dice. So now suppose I'm rolling 2 6-sided dice. It gives me values D1 and D2. Let event E be that my first die lands on a 1. Let event F be that my second die lands on a 6. Let event G be that the sum of the 2 die is 5. Let's see first, are E and F independent? And secondly, are E and G independent? Take a minute, put it on pause, and see what you come up with. I want you to show it to me mathematically, even if you have some intuition about this. All right, first, so let's think about what these sets are here. So the way I could get a 1, I could get a 1, 1, I could get a 1, 2, I could get a 1, 3. These are all the possible ways I could roll a 1 first. And so you can see those here as basically the top row. If I think of red as being the first die, this top row gives me those 6 possible outcomes. So the number of outcomes in E is 6. Similarly, the number of outcomes in F is also 6, because that's assuming my second die roll was a 6, and there's 6 ways that could have happened. So if I want to think about E and F together, let's think about the way that I could get a 1 first and a 6 second. There's only one outcome that has that here, right here. So if I think of probability of E and F, and I'm doing it by equally likely outcomes, that's 1 out of my total sample space of 36 possible outcomes. And then we're going to notice the question mark is, does that equal the probability of E times the probability of F? Well, this is 1 out of 6, or 6 out of 36, right? Which is going to simplify. So let's write it like that first. 6 out of 36. This is also 6 out of 36. And yes, we can see that the product of those does give me 1 out of 36. So yes, this is independent. What about E and G? So again, let's do each of these pieces here. I know probability of E was 6 out of 36, which is 1 out of 6. I need to look at the probability of G, and then I'll look at the joint probabilities, and I'll see if they are equal to this product. Okay, so let's fill in now these remaining pieces. Probability of G. So let's look at what outcomes are in G here. In order to add up to 5, I could do 1 and 4. I could have 2 and 3. I could have 3 and 2. Or I could have 4 and 1. Those are the only 5, or the only 4 possible ways this could happen. So 4 out of 36 means there's a 1 in 9 chance here. Okay, but now the probability of E and G. So if I know my first die is a 1 and the total has to add up to 5, well, there's only one way that could happen. It has to be the roll 1, 4. So that's a 1 out of 36. And so I can see now that this is not equal to the product of the individual probabilities. And so this is not independent. These are dependent. Another way you can think of this, again, it's not changing any of the math, but it's just adding this joint probability table back into how you're thinking about this process. So if we think of the probability of E as adding up the 1 and the 5, so I'm getting 6 out of 36 here. Looking at the probability of F is also 1/6. This is the totals. Then in order to be independent, I need the product of these totals to equal the joint probability in the middle of the table. And I can notice that one small change to the table will change whether or not it's independent. So again, this row looks the same here with E, but now with G, you can see my total here ends up being 1/9. And now the 1/6 times the 1/9 does not equal the middle. And so this is an example of two events that are not independent. Let's try a third. So now let's define another event. This time, instead of having the die add up to 5, let's have them add up to 7. Go ahead, put it on pause, and tell me if you think these are independent. All right, so here's an example where your intuition might deceive you, because originally you'd think, well, it should depend on the first die, because knowing what the first die is should affect, the sum, which is what we found here. We found E and G were dependent, but now there's something curious that happens with H. I want you to think of the number of ways I could add up to 7. So I could get 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. Aha, so there's something interesting about that because there happens to be exactly 6 ways that I can add up to 7. And why is that interesting? Well, notice my probability of E was 1/6, 6 out of 36. My probability of H now is also 1/6. And what's my joint probability of getting E and H? Well, if I know the first die is a 1, there's only one way I can add up to a total of 7. I have to get a 1 and a 6, so that's a 1 out of 36. And in this case, it is equal to the product of the individual probabilities. So this one is independent. And that's an example of where your intuition may have deceived you, and it's important to use the actual definitions before ever making conclusions. Now, let's think of extending this idea. Right now, I've just been looking at the independence of 2 events, but a lot of times I'll be doing more than just 2 trials. I'll be doing n trials, and I want to make sure all n of those trials are independent. So when I'm defining independence for more than just 2 sets, I actually have to look at all possible subset combinations and make sure they are independent. So let me show you an example on the next page, but common things we'll use in this class is like, oh, I'm flipping a coin n times, or rolling a die n times, or sending a multiple choice survey to n people. Those are all going to be considered n independent events. But mathematically, we show that as follows. So 3 events, E, F, and G, are independent if I have to show all possible combinations. So not just the pairwise ones, but I also have to be able to do the probability of E, F, and G equaling the product of those 3 probabilities. And it gets even more when I add more events to this. I have to look at every possible subset combination and show that this is true. So this can be very hard to prove independence for more than just 2 events, unless it's something like simple like a dice rolling or flipping coins, where it's easy enough to be able to extend the idea. Okay, so let's look at an example here where it's harder to see whether or not I have independence between these 3, E, F, and H. So notice, to show that E, F, and H are independent, I would have to show all possible pairwise combinations, E and F, E and H, F and H, and then E, F, and H. I've already shown E and F are independent, and we actually just showed in the last example that E and H are independent. So yes, that was our last example. Okay, let's look at F and H and then all 3. So let's do probability of F. Okay, that's 6 out of 36. Probability of H, we showed last time because it has 6 possible outcomes, is also 1/6. Probability of F and H. So let's see how that's going to work. Well, the second die has to be a 6 and the sum has to be a 7. So that means the only possible outcome that satisfies that is this one. So there's only 1 out of 36. And we can see that is equal to the product of the 2 individual ones. So yes, this is independent. So far, okay, these 3 are looking good. But we now have to test this 3-way independence. So now I need to look at the probability. Well, let's look at all 3 of them. E, F, H, and then I need to look at the joint probability. Probability of E, F, and H. And I want to see if that's equal to the product of all of these. Okay, so probability of E we already have, 1/6. Probability of F, 1/6. Probability of H, 1/6. So the product of all of these is 1/6 cubed. Now I need to see is, so let me put this here, question mark, does this equal 1/6 cubed? That's the question mark. Okay, now we need to see the probability of E, F, and H. So now I need to see how many outcomes have dice 1 is 1, Dice 2 is 6, and the sum of them is 7. Well, there's only one outcome, 1 out of 36. Okay, and I can see that this is not equal to 1 over 6 cubed. So these are not independent, which means in general, E, F, and H are not independent. So this is tricky, right? This is pointing out that pairwise independence, having all three of these boxes checked here, is still not enough to prove independence of all three of those events. Let's try another example. Okay, so now I'm going to tell you in advance that I have n independent routers. So this is nice. You don't have to test it. I'm telling you they're independent. They each have a probability p sub I of functioning. So think of this one as probability p sub I of working, this one p sub 2, this one p sub n. E is the event that there's some functional path. So I'm able to get from here some way to here. And maybe more than one, right? But there has to be at least some functional path. What is the probability of E? Go ahead, put it on pause and see what you come up with. All right, here's an example where I can think of lots of ways that I could get a functional path, and I don't want to have to go through all of those scenarios and add them up. So let's actually calculate the probability of E by doing 1 minus the probability that none of them work. 1 minus probability all the routers fail. Okay, well, what's the probability the first router fails and the second router fails and the third? Well, because they're independent, I can then just take the product, right? The probability you want to think of, I'll think of first fail and second fail and third fail is the product of each of those probabilities. And that's what we're showing because they're independent. That's what I'm showing right here. And then this is just fancy math notation for saying take the product of everything that's inside here. It's like sigma notation with sums, but it's just saying take the product of this 1 minus P1 times 1 minus P2 all the way up to n. So independent trials, in this case, independent routers, is going to simplify a lot of our calculations when we're able to assume we have independence. All right, our last example is going to clarify some common misconceptions. So first, I want to know, suppose you have two events, and let's assume that the probability of each of them is greater than 0. We're going to just start with that. Okay. Given that, so is it true that they're independent if knowing that F happens means that E can't happen, or knowing that F happens doesn't change the probability that E happened? So think through both of those first, and we'll come back. All right, so your intuition for B is basically the definition. Knowing that F happens doesn't change the probability that E happened, so probability of E given F is still probability of E. That means, yes, they're independent. So yes, that's true. Okay. But what about A? Knowing that F happens means that E can't happen. Well, that means that the probability of E given F is actually 0, because knowing that F happens means that E can't happen. Probability of E given F is 0. That does not imply that the probability of E happening was also 0. Right? So it's not equal to the probability of E. I have no guarantee here. So I'm going to say that's not equal to the probability of E, especially because I also told us that all of these are non-zero. Okay, so this is a false statement about independence. In fact, knowing that F happens, telling you if F happens and E can't happen, well, then they're definitely dependent, because knowing something about F tells me automatically what happens with E. All right, second question. Are E and F independent in the following pictures? Okay, so this is also just to give you a real warning that independence is often hard to visualize graphically. So we're going to mathematically look through these scenarios. So first, let's look at this scenario. And this is meaning a probability here, this 1/4 and this 1/4. These are my events, and I'm saying they have a 1/4 probability. Okay, so here I have the probability of E is 1/4. The probability of F is 1/4. But the probability of both of them, because I'm showing them as mutually exclusive, is 0. Okay, and so I can see right now that's not equal to the product of both of them, so these are dependent. So not independent. They're dependent. What about in B? So again, I'm going to have to do this mathematically to see. Just because I have some overlap here, I can't necessarily conclude that they're dependent. Let's see what happens. So here my probability of E is going to be 2/9 plus 4/9, 6/9, or 2/3. My probability of F is this whole part here, is 2/9 plus 1/9, so 3/9, or 1/3. And then let's look at both. The probability of E and F, so I'm looking at where they intersect, is 2/9, just this part here. Okay, and now the question is that equal to the product of both? So 2/3 times 1/3, yes, is equal to 2/9. So yes, these are independent. So yes, E and F are independent. So this is just to clarify and make it maybe emphasize that just because you have disjoint events, mutually exclusive events, does not mean they're independent. Okay, and just because you have some type of overlap in your picture, you have non-disjoint events like this, doesn't necessarily mean that they're dependent. You need to actually do the math in these situations, and independence can be very difficult to visualize graphically. That's our ending of this intro to independence. We will be revisiting this idea of independence when we move on to random variables in the future.